Hello everyone, my name is Mengqi. Today I'm going to talk about a covert timing channel in safety-critical systems. So modern cyber-physical systems integrate multiple applications into a high-performance system chip to reduce communication complexity and hardware cost. When integrating these applications, it is important to provide temporal isolation among them so that high-critical applications can be protected from low-critical, potentially faulty applications. Temporal isolation is achieved by partitioning the CPU time. That is, each application is given a guaranteed amount of CPU time, so we can isolate potential misuse of CPU, and also we can reason about individual applications' temporal behavior independently. So how can you partition CPU time? Real-time hierarchical scheduling is a class of scheduling approaches where a scheduling decision is made in two steps. First, the global scheduler picks a partition according to the global scheduling policy. Here, a partition has a number of local tasks. Then, the local scheduler of the selected partition schedules its local tasks according to its local scheduling policy. This way, each partition has an illusion that it has an exclusive access to the CPU. But from a security perspective, hierarchical scheduling fails to achieve temporal isolation, although applications are completely isolated from each other in the utilization of time. So in this paper, we showed that partitions can form an algorithmic covert timing channel through hierarchical scheduling, and also show how such a channel can be removed by a scheduling approach. In this paper, we consider non-static time partitioning, where partitions are scheduled by priority. Each partition also has a budget, like how much CPU time it can use during a time interval called replenishment period. Non-static partitioning approaches are more flexible than static partitioning in that it can achieve higher CPU utilization and better responsiveness. But this flexibility is actually what enables the covert timing channel between the partitions. So how can a non-static partitioning be exploited as a covert timing channel? So let's consider two partitions, sender and receiver. The sender wants to signal 0 or 1. Here, the sender partition has a higher priority than the receiver, and the receiver partition has two tasks, R1 and R2, and these two tasks share a counter C. And R2 has a higher priority than R1. Now, R1 starts at time t0, then it reads the value of the shared counter, and then starts a loop. Later, a task of the sender partition arrives. Because the sender partition has a higher priority, it preempts the receiver partition. Now task S1 starts its execution, and its length depends on what signal it wants to send. Let's say it wants to send the binary value 0. Task S1 runs and then finishes. Then the receiver partition takes the CPU, so task R1 resumes, and at the end of this execution, it reads the value of the count again. At time t2, task R2 arrives, and its only job is to increment the counter variable by 1. But R1 has already finished, so R1 has read the counter value twice, but it remained the same. Now, for the sender to signal bit 1, it executes longer, just longer enough that R2 arrives before S1 finishes. And this time, when the receiver partition takes the CPU back, task R2 starts its execution because it has a higher priority than R1. So the counter is incremented as soon as task R2 executes. So when task R1 resumes and finishes, it sees that the counter value has incremented by 1. From this, task R1 infers that the sender partition has signaled bit 1. And here you can see that no time information was used to make such an inference. So why is this communication possible? That is because the receiver's local schedule changes as the sender changes its behavior. So our idea to remove this covert timing channel is to make the partition local schedule deterministic no matter how other partitions behave, and this is done in the runtime by our algorithm that we call blinder. So how does it work? Let's see this example, which is similar to the earlier one. Task I2 has a higher priority than I1, so it would run at time t3 when the preemption ends. But that made the Covert channel scenario possible. So the key idea of blinder is that we defer the release of task I2 as if the partition level preemption did not happen from task I1's perspective. For this, blinder adds arrival queue to each partition, and every newly arrived task are put into this arrival queue, and blinder releases them at the right times. That's the only change made by blinder. The local schedule itself is not affected at all. So what does it mean by the right time for task release? If the preemption did not happen, task I1 would have additionally executed for delta y from time t1 until task I2 arrives. So the release of task I2 should be deferred to ensure that task I1 makes the same amount of progress no matter how long the preemption by partition J is. This also applies to tasks like I3 that arrive while partition is active, that is not during a preemption. But what about task I2 at time t8? It shouldn't be deferred because all the prior executions of partition I that were affected by the partition level preemption by J complete before t8. So this second arrival of task I2 does not change the local schedule of partition I. So it is released immediately. So what's happening here is that blinder enforces partition local schedule to follow the partition's canonical local schedule, which is the local schedule when no other partitions run. But the canonical local schedule cannot be statically constructed because tasks may arrive at arbitrary times and they may have variable execution times. And these are unknown until they actually execute. And these in turn affect how the partition budget is used. So blinder constructs a canonical local schedule on the fly. For this, blinder maintains a state variable called task release mode for each partition. It can be either normal release mode or deferred release mode. When in the normal mode, it's basically the vanilla scheduler without blinder. Now, the partition enters the deferred release mode when it is being preempted by a higher priority partition. This is when the local schedule starts deviating from the canonical one. When in the deferred release mode, newly arrived tasks are put into the arrival queue and they are released later. Partition switches back to the normal release mode when all the tasks that have arrived before or during the deferred release mode complete their executions. So this is when the local schedule is synchronized with the canonical one. So now, how is the task release time decided on the fly? It's when the lag becomes 0. Lag is a per task counter, and it is initialized at task arrival using per partition variables called available time and use time. Available time is basically the maximum amount of time that would have been available since entering the deferred release mode. Use time is what has actually been used since then, and it is simply a counter. Lag is the difference between these two. That is, how much the current local schedule lags behind the canonical one. If it is not 0, say 5, task release should be deferred until the partition executes for 5 more time units. So lag is reduced as long as the partition runs, and when it becomes 0, the task is released. So in the previous slides, we assumed no budget limitation, but the available time is actually limited by partition budget constraint. And I'm not going to go into the detail, but the idea is that available time can be calculated by assuming that all the budgets are used up as soon as they become available. Now, blinder adds some delay to task release. So a natural question would be, will it affect the schedulability of real-time tasks? And the short answer is no. Basically, what we proved in the paper is that if a partition is schedulable, that is, if the full budget is guaranteed over every replenishment period, blinder does not increase the worst-case response times of tasks. So what this means is that tasks are schedulable if they are so without blinder, which is important especially for real-time systems. So we deployed blinder on an experimental real-time system that runs Litmus, which is a Linux-based real-time operating system. And the system has 4 partitions. And with these, we are able to demonstrate a covert channel between the navigation partition and the hash monitoring partition, and also show how blinder closed the channel. And as you can see from the timing diagram on the right-hand side, blinder guarantees that receiver 1 task finishes before receiver 2 task execute, no matter what signal the sender partition sends. So the receiver always sees the same signal. We evaluate the impact of blinder on the responsiveness of real-time tasks using a synthetic partition set. We compare 3 methods: the static partitioning, the default non-static partitioning without blinder, and with blinder. I'm going to highlight only some important points here. These graphs show the worst, best, and average case response times. First of all, you can see that blinder does not increase the worst case response times as explained earlier. But blinder may increase the average case response times. And you can notice that from the highest priority tasks of partition 2, 3, and 4 in these graphs. And this is because without blinder, they would always be released immediately, but with blinder, they are released delayed during the default release mode. But for low priority tasks, the impact is small or none, because from their perspective, the delay due to lag is not different from delay due to higher priority tasks. So we have talked about blinder, which is a runtime schedule transformation technique to close algorithmic covert timing channel over hierarchical scheduling. Blinder preserves the flexibility of non-static partitioning schemes while achieving the partition-obliviousness that static approaches would provide. Blinder is backward compatible and minimally intrusive in that no modification is required to global and local scheduling policies, which is attractive to existing safety-critical systems that require high recertification cost. So with that, thank you all for your time, and I look forward to answering your questions.